Digital signatures provide for the ability of a signer to create an attestation of a message that can be verified by a verifier. Digital signatures are used in Bitcoin applications for a number of purposes, including within very common script templates for Bitcoin transactions. They are also used to attest to the validity of documents and other digital assets that people interact with when they use Bitcoin-powered applications. Therefore, applications and wallets should agree on a standard interface for the creation of digital signatures within Bitcoin-powered applications in the most open-ended way possible, so that application developers can define systems that create digital signatures in a cross-compatible way with different wallets and other applications. In this video, I will describe what I believe to be the most open-ended way for creating digital signatures as part of a Bitcoin wallet-to-application interface specification. This is the third in a series of videos that I have done on this topic. The first video defined the core of the specification with creating Bitcoin transactions and dealing with Bitcoin tokens. The second one talked about data encryption and introduced protocol IDs and key IDs and identity keys for users, as well as the derivation of child keys. I recommend watching both of those earlier two videos before proceeding to this digital signatures topic. We would want to start by defining two more functions within our wallet-to-application standard interface specification. The first of these functions would, of course, be for creating a digital signature, and the second would be for verifying a digital signature. Now, why, once again, are we doing this inside of a Bitcoin wallet-to-application interface? I think that the reasons that I provided within the data encryption video are valid. And in addition to those reasons, which are equally valid for digital signatures as they are for data encryption, we would also benefit from having digital signatures as part of this because, in addition to being able to sign just normal documents and other things like this that applications might want to use, you can also sign Bitcoin transactions themselves. So users can derive keys and then use those keys to lock up Bitcoins in certain output scripts for various tokenization schemes conforming to various protocols that exist within applications, and then use ECDSA, the elliptic curve digital signature algorithm, to produce digital signatures that unlock the coins and satisfy the unlocking conditions of the UTXOs that originally used those particular keys that are held by users. So, we have the data to sign that is passed in to the creation function, the function that creates that digital signature, and as a return value, we receive the signature itself, encoded in some standard format. Let's use DER. That's common in Bitcoin. So a digital signature is returned to the application from the wallet or service provider when the application requests that a signature be created and provides some data to sign. In order to prevent extremely large data from being moved across this boundary and then back again needlessly, it would also be possible for the wallet, or rather the application, to provide the wallet with just a hash of the data, which is then directly used by the signing algorithm. thereby reducing message sizes and bandwidth potentially. So we can make that optimization in the signing function. Now, similar to encryption and decryption, we should also define a set of key IDs and protocol IDs so that signatures created within one protocol are verified within that same protocol given the same key ID. So the verifier can use the verify signature function with the identity key, not the signing key, but the identity key of the signer, and then the protocol ID and key ID for the protocol that was used to create the signature, and then can achieve sort of a result where they receive a Boolean from the verification function indicating whether or not the signature over that data is valid. So the verifier would derive a child key from the identity key of the signer based on the protocol ID and key ID that are being used, and would then use that child key to verify the actual signature. Conversely, the signer, when they create the message, the signature rather, would derive the corresponding private key using the same elliptic curve math, or converse elliptic curve math for private keys, and would then be able to produce a signature valid according to the verifier for that converse public key. So we have a method by which this can be done. And for encryption, so we have single party encryption, which is counterparty of self, and then we have encryption for a particular counterparty, a recipient of data in encryption. But in this context, we might want another option. So encrypting, it doesn't make sense to have counterparty all so that everybody could decrypt, because then what's the point of encryption? But with signatures, it does make sense to have a signature that anybody could verify. Now, we would never directly sign something with a user's private root identity key. So in the case of counterparty all, we just use a well-known private key, derive its public key, and use that public key as the counterparty. So everybody knows what the counterparty's private key is. Everybody can derive the corresponding signing key as if the counterparty was them specifically, and then everybody could verify the signature. So in this context, counterparty all, let's just agree that the private key is 1, and the public key can be 1 by g, which means you multiply by the generator point of the elliptic curve, and you get the public key that is the counterparty used in counterparty all signing operations. So that when a signature is produced, you can pass in the protocol ID, the key ID, the counterparty, which by default is all, so that anybody can verify the signature, and of course the data or the hash to sign, and retrieve back a result that includes the signature in DER format from the wallet. Now, the reason why we picked DER format is because that's a common signing thing inside of Bitcoin that everybody kind of uses for signatures. You get the R and the S value. And protocol and key ID have been explained in the data encryption video, how those work. This allows for applications to sign under specific protocols. And then the verify signature function, you should provide counterparty of the signer. So you always provide the counterparty and verify signature. Somebody signed, whether it's you or somebody else. The default counterparty and verify signature is going to be the self, so that you can verify your own signatures. But if you don't provide that, then you'll want to provide the public key of the person who signed, the identity public key. And then it would also require protocol ID, key ID, and the data to the signature, of course, to verify, and the data or the hash that was signed. So that's how a signature verification and signature creation works within the context of this system. This is surprisingly open-ended because now we have entire key universes not only to sign something with under a specific protocol, but with a specific counterparty. So that when I create a digital signature, I can set it to a specific person who is the counterparty, the verifier, and then only that verifier can check the legitimacy of that signature. Because given my identity public key, the verifier needs to be able to calculate a shared secret, which is used as an offset in conjunction with the protocol ID and the key ID, from my identity public key to derive the key that I used for the signature. I don't directly reveal that signing key to anybody. I assume that the verifier has the ability to calculate it. And therefore I have the ability to create signatures that only a certain person can verify. This can be extended, and in fact is extended, by higher level systems that build on top of this functionality. Things like Authright for establishing secure communications channels between parties, dealing with identity certificates, etc. But within the context of the creation and verification of digital signatures within a Bitcoin wallet to application interface, these are the functions that emerge. We do find ourselves with one final loose end to tie up here, though, which is that we want a way to know public keys, right? So I want a way to discover the public key of a foreign user that, for example, has sent me something. So we can define a get public key function where I provide the counterparty, being the foreign user, and then I provide the protocol ID and the key ID. And then what I do is I derive a child key based on my private key and the counterparty's public root identity key and the protocol ID and key ID. And then that offset key, that child key for the counterparty, can be returned directly to me as the person who is deriving this person's public key. And this can be used in a number of applications, including sending tokens and other data on the blockchain that can be unlocked by that counterparty. So the get public key function does that, and then there's a for self parameter where now I'm deriving a public key of my own, a child key of my root identity key, and when this for self parameter is true, now if I'm the counterparty, I can derive that same public key. So like if I want to give my own child key to somebody else, or check that a child key which they derived for me matches what I expect. So it is possible to derive your own child public keys using the get public key function as well. There are a number of use cases and things that can be applied for these types of functions. The get public key function, when you use counterparty of somebody and then you provide for self, so you're saying give me one of my own child public keys, can be used, for example, to verify that a particular token has been received and sent to the correct public key, so that when somebody sends me a token, for example, to my a derived child key within a particular token protocol within an application, I can verify that given the key ID and protocol ID they use and given their counterparty, they properly derived my key. And I can know that when I later go to redeem that token by using create signature to sign the SIG-hash pre-image of the Bitcoin transaction that spends the UTXO which they sent to me, I'm able to successfully do that because it is my public key that they used and I was able to verify it. So applications for this are very open-ended. They are not just limited to simple document signing and verification, but now applications have the power to define any number of architectures within specific protocols and then request permission to use those specific protocols. So users can control which signing protocols applications can access when digital signatures are employed over their data. That's essentially all I have to say in this video about digital signatures. Digital signatures are a fundamental component of the wallet-to-application interface because they enable functionality related to the locking and unlocking of Bitcoin tokens, but also because they're useful in the wider context of application development where users are at the center of the equation for the application. So things like a user wanting to verify a signature over a document which they're interested in. I think I'll leave it here. So thank you for taking the time to watch this video about digital signatures. I'm not sure what I'm going to cover next time, or even if there's going to be a next video in this series. I'm going to wait and put my ear to the ground, listen for some feedback from the industry about these types of capabilities and functionality. And I would like to start a discussion with industry about whether it makes sense to standardize the barrier, the interface, the boundary between wallets and applications. And I hope it doesn't act as a barrier between these two things. I hope it makes it easier for more types of applications to get created. That's always the goal. We need to ensure the widest possible compatibility and interoperability between wallets and applications. And we need to be very conscious of the long-term implications of architectural decisions that get made in the context of barriers between applications and wallets. So thank you for watching, and I look forward to your honest feedback.